All right, so far we've looked at the distance problem, we've looked at the area problem, and we've seen that to kind of estimate distance traveled, or total area under the curve, involves adding up a whole bunch of terms. And so we want a notation that just kind of simplifies these equations a little bit to clean them up. And so the notation that we commonly use when we have the sum of a whole bunch of terms is called sigma notation. So sigma notation here gives us a way to write sums with many terms a bit more compactly. So the way we generally use it is, this is sigma. Think of it like a big plus sign. So we're adding up. When you see a big sigma here, it means we're adding up a whole bunch of things. And so that's probably the first thing to note. The sigma here tells us to add. Okay, so that's our sigma notation. Now we also have, there's some indexing that usually goes on. So I, in our notation here, I is an index. It's an index number. Don't always have to use I. Sometimes we use J. Those are pretty common indexing numbers. So the I here that you're seeing is our index. And it's usually a integer. It's usually an integer. Usually a non-negative integer. So most of the time we're going to be talking about integers really starting at 1 and then going up to some larger integer n. So in our notation here, this I equals 1, that portion tells us where to start, the starting index. So we're going to start with I equal to 1. And then the number up here, this n, that tells us where to end. So we're going to end at index when the index number I is equal to n. And so we're doing the summation from I equals 1 to n of a sub I. And if we were to write that out, what it would be equal to is it would be the A1 term plus the A2 term plus the A3 term plus the A4 term, and you keep going up until you get to the AN term. And that's where we end. So we end with the AN term right here. All right, so that's sigma notation. It gives us a way, instead of writing it out, A1 plus A2 and so on, if we have a whole bunch of terms, we can write it in this more compact notation as the sum from I equals 1 to n of A sub I. And we've looked at the distance example, and in that distance example, what we did is we had the velocity at time 1 times delta t, plus the velocity at some other time, t2 times delta t, plus the velocity at at time t3 times delta t, up through the velocity at time t6 times delta t. So this is what we did in our first example. So we were adding up essentially 6 terms here. And so a way to write this out that's just a little bit more compact, especially so we don't have to put these dots here, or have a really long line of everything just written out. Another way to write this is we could write this as the sum from I equals 1 to 6 of our velocity at time t sub I times delta t. So this just gives us a way to kind of write this in a more compact form. And so this is where we used n equal to 6 subintervals. And this t sub I, what was t sub I? That was these t sub I values, those were the left endpoints for each of our subintervals. And delta t, what was delta t? That was the width of each time subinterval. All right, so in our notation here, these t values, those we ended up using as the left endpoints, and then delta t was the width. Now, in the area example that we did in the last one, there we had 3 approximating rectangles that we calculated the area of. And so, you know, writing a sum of 3 terms is not too bad, but if we wanted to write this out in sigma notation, how it would look is it would be the sum from I equals 1 to 3 of f of xi times delta x. So we're adding up. What are we doing? We're doing a sum from I equals 1 to 3 of f of xi times delta x. So we have f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x. And for this one, the xi values, we didn't mention it, but those were actually midpoints. Go back and take a look at that in a second. And delta x was the width again, so of the subintervals. So let's go take a look here. And this is where we're using n equal 3 subintervals. So we're adding up 3 terms, essentially. So let's just go back and look at those midpoints. So here is this previous example with the 3 approximating rectangles that we did. Here was the kind of the sum written out. And what did we use? What were the x values that we used? Well, the first subinterval was from 1 to 3, and we used 2 as the place to get our function value. And then our second subinterval was from 3 to 5. And what was the x value we used there? 4, right in the middle. And then what about the subinterval from 5 to 7? What was the x value we used there to get our function reading? That was 6. We used the 6th location to get our function value. And so when we have our subintervals here, and we use the kind of the halfway point, the midpoint, we call those midpoints. So for instance, this first subinterval was from 1 to 3, the midpoint was 2, and that's where we used to get our function reading. The second midpoint was at 4, and that's what we used to get our function reading. So we didn't use the left endpoints. We didn't use 1, 3, or 5. We didn't use the right endpoints of 3, 5, and 7. What we did is we used the midpoints, 2, 4, and 6. And so the question is, we have some choice. Generally, if we're going to do these type of approximations, we have some choice about if we're going to use left endpoints, if we're going to use midpoints, or if we're going to use right endpoints. And so this is really going to kind of get us to our idea of Riemann sums. So what we're calculating in each of those instances, in each of those cases, the distance and the area, is what we call a Riemann sum. And so this is when we calculate the sum from I equals 1 to n for some number of sum intervals here. So again, think of n as the number of subintervals. And what makes this a Riemann sum is that we're doing this summation of f of xi star times delta x. So it's f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x, and so on up until we get to f of xn times delta x. And then we add all those together. And this is our Riemann sum. All right, so the control here is, or what we have some control over, is these x values that we're plugging into our function. So xi star is how we actually figure out what xi star is we pick a number from the ith subinterval. So we're going to have this interval from A to B, as we've been doing. We're going to slice this up into a whole bunch of smaller subintervals, just like we've been doing. And we're going to look at the ith one. Well, so we have our first subinterval here, we have our second subinterval, we have our third one, and so on. And so for our first subinterval, say, we're just going to pick some number in that subinterval. So for this first subinterval, x1 star gets picked from that first subinterval. Then we go on to our second subinterval. We pick a number from that one. We call it x2 star. And it could be anywhere inside that subinterval. Go to our third subinterval, pick another x value. We call that x3 star. So it could be anywhere in each of these individual subintervals. And the way we calculate the width, this delta x value, we want to think of it as the width, is delta x is b minus a over n. So it's the width of our subintervals. And normally we make them all have the same width, just to keep the calculations easier. And you see that as n gets bigger, so as you use more and more subintervals, what's going to happen is delta x is going to get really small. All right, so this is our formula for Riemann sum. The x values are just a number that we pick from the ith subinterval. So for instance, our first subinterval, we would pick x1 star, just some number in there. And that's what we're going to plug into our function then. And delta x is b minus a over n. So it's the endpoints of our big interval here divided by n. And that gives us the width for each of these small subintervals. All right, and we call these sample points. These x star values, we call them sample points. So we could just kind of go through and pick whatever we want, but normally we like to be a little bit systematic about it. So normally we use either right endpoints, left endpoints, or midpoints. And so the right endpoints, if we had our subinterval, So here's our subinterval. The right endpoint means we're just going to pick the right endpoint. The left endpoint, if this was our subinterval, little section of the x-axis here, the left endpoint, you just pick the left endpoint. And midpoint, you pick halfway in between. So, you could, if you wanted to get crazy, you could just kind of pick anything inside this subinterval. But normally we want to be systematic about it. So when we go through, we just consistently pick all right endpoints or pick all left endpoints. So how would that look? So if we had our interval from A to B, and we have all of our little subintervals here, what would it look like when we actually go through and pick the right endpoint from each of those? Well, from this first subinterval, if we use the right endpoint, it means we're using this. And then we have our second subinterval right here, but we're going to use the right endpoint for that one, and so on. And we keep going until we get to our last subinterval and we use the right endpoint there. So just to give a little picture for what it might look like on our subinterval lines here. All right, so how do we actually calculate these? Well, for our right endpoints, we want to start, well, for all of these, we want to start with kind of the first one, and then the rest of them, once we have the first one, the rest of them are going to be easy to find. So for the right endpoint, we're going to use A. So remember, our interval is from A to B. So it's going to be A plus delta x. And then to get the rest of them, we just add in delta x each time. So for x2 star, what do? We just add delta x. So we take our previous result, A plus delta x, just add another delta x to it. So this would be A plus 2 delta x. And then to get A3 star, what would we get? Well, we just take our previous result and add another delta x. So this would be A plus 2 delta x plus delta x. So 3 delta x's. And you can probably see the pattern here. And you just keep doing this until you end up with, so you kind of keep going with this until you get to xn star, which is going to be B, the right endpoint of the entire interval. Now, if we're going to use left endpoints, also perfectly fine. So there, process is going to be very similar. It's just for the left endpoints, we're going to start with just A. So for the right endpoints, we start with A plus delta x. For the left endpoint, we're just starting with A. And then we kind of repeat the process and get x2 star, x3 star, and so on. And how we kind of get the next one is we just add delta x. So if this is our starting x1 value, well then x2 in this case is just going to be A plus delta x. Now to get x3, we take our previous results and then just add in delta x again. So A plus 3 times delta x. Or 2 times delta x, sorry. So we had one copy of delta x, now we're adding another one, so we have 2 copies of delta x. And we just keep repeating this up until we get to xn star, which in this case, we're not going to get all the way to B, we're going to get to A plus n minus 1 times delta x. So you just kind of keep adding in these copies of delta x up until you get to here, until you have n of them. All right, what about midpoints? So for midpoints, again, it comes down to just knowing what the starting sample point should be. So for midpoint, it's A, but then we want to go halfway across. We want to do half of this width here. So this would be our starting A value, and then we want to do half. So it'd be A plus delta x over 2. And then once we have our starting value, the way to get the rest of them is you just keep adding delta x's. So to get x2 star, we're just going to take A, and then we have delta x over 2 plus delta x. And then to get x3 star, what are we going to do? We're just going to add in another delta x, and that'll give us our x3. So we'll have A plus delta x over 2. And then we had a delta x. We're adding in another one, so we'll have 2 delta x. And if we wanted to get a common denominator, we could kind of combine these. And then we keep going, and we keep doing this, keep adding delta x's to get each of our, the rest of our midpoints. And where we should end up with here is we're going to end up with our nth sample point, which should be A plus delta x over 2 plus n minus 1 times delta x. But again, I really wouldn't have these formula memorized for the different endpoints. What I would have is just the process. So for the right endpoints, just know that we start at A plus delta x, and then we just add in these delta x's. For our left endpoints, we just start with A and then add in the delta x's. And then for the midpoints, we find the first midpoint, and then to get the rest of them, we just keep adding delta x's. All right, so a little bit of notation here, getting these notation for our Riemann sums set up. And we're going to see why this becomes important in the next portion here. So we'll see you there.